All right, gang, here we go. This is for Physics, Unit 7, Part 5, talking about sound, intensity, and resonance. Okay, um, just a heads up, if you're watching this in the year 2019, part of these notes go into Part 6, but they're changed in the future. All right, anyway, so sound intensity, we just talked all about sound. We talked about a bunch of new ways of thinking about sound, but specifically we need to talk about something called intensity. Okay, and intensity is defined as I forgot my pen. Okay, intensity is defined as the rate of energy flow through an area. Now, let's take a step back and think about something real quick. In order to create sound, something vibrating is pushing against the air, right? And it's usually vibrating very, very quickly, right? Right? Okay, so it's vibrating very, very quickly and it's pushing those molecules. As it's vibrating, it's applying a force and moving those air molecules a distance. So essentially what it's doing is it's doing work on the air molecules. And that makes sense, right? Work is force times distance. Okay, so the vibrating object is doing work on the air. Work is in joules, right? Joules is the unit for energy. Okay, so essentially when we create sound we're using energy, right? We're pushing energy. Okay. Sound is energy. Okay, so intensity is the rate of that energy flow, and then specifically we care about it through an area. That's the intensity part of it. Okay, now remember, way back several units ago, we talked about the rate of energy flow, and we called that power. Okay, we said that was the energy per unit time. We talked about how, like, if you had a more powerful engine, it would do work faster, not more work. It would just do that same amount of work faster because it had a higher rate of energy flow. Okay, so it had a higher power, and then the less powerful engines would do the same amount of work but a lot slower. All right. Now the tricky part here is because we care about it through a specific area. Specifically, a lot of time when we're talking about sound, we care about the area going through our ear canal here. Yeah. Okay, because that's where we're going to hear. We want to make sure it doesn't hurt us, or if it's not loud enough to make us warn us of danger or something like that. Okay, and so we have to think about, well, what is that area that we care about? Now remember, our waves, we just talked about how our waves, they spread out as spheres, right? They equally spread out in all directions from whatever the source is. Okay, and because they spread out as spheres, the area that they're flowing through would be the surface area of a sphere. And this is the equation for the surface area of the sphere. Area equals 4 pi r squared. All right, so here's your formula for intensity. Okay, your intensity is your power, your energy flow through surface area, 4 pi r squared. Okay, so, all right. The SI unit is watts, right? That's the unit for watts. Remember, watts, a watt is equal to a joule per second. Okay, so anyway, so a watt per meter squared. So that's your intensity units. All right, now this is an inverse square relationship. Now this is where life gets exciting. I'm pretty sure we haven't had an inverse relationship, or we have had an inverse relationship and a square relationship, but never at the same time. And this makes the math a little bit more exciting. Okay, so let's think about this. So doubling R reduces the intensity by 1/4. So let's see what would happen here. If we have our intensity at some value, and we've got our P over 4 pi, right? But we've doubled our R. Okay, so our R is 2 times the R that it was, right? So then we could simplify that. Well, that becomes P times 4 pi times 4r squared, right? So notice this 4 was not here in the original equation. So therefore, but it's on the bottom, so the intensity would be 1/4 as much. So essentially what we're saying is that if you double how far away you are, remember, because the r is the distance from the source, if we double our distance from the source, all right, it will be here, the intensity of the sound will be 1/4 what it was. Okay. All right, and what happens if it's halved? So if our distance is halved, that means we're twice as close as we were. Let's do that again. All right, so our intensity is equal to pi over 4, P over 4 pi, and this would be R over 2 quantity squared. All right, so if we carry that out, that means our intensity would be equal to P over 4 pi times R squared over 4, right? And these 4's would cancel. So essentially what we'd get is our intensity is equal to our power divided by pi r squared, right? And that 4 is not there anymore. So essentially what we've done is we've multiplied by a factor of 4 and made that 4 cancel. Okay, so it's pretty wild. All right, now, once again, just like we did before in our previous video, we care about human perception. Okay, this is important because humans deal with sound all the times. Okay, and they don't really care about intensity, watts per meter squared, and stuff like that. So we use an intensity scale that's based on human perception of loudness, and this scale is called the bell, or the bell. Okay, more commonly it's referred to as a decibel. Okay, or a decibel. All right, and so essentially a decibel or a decibel is 10 times 1 bell. Okay, so 5 bells would be 50 decibels, etc. All right. On the decibel system, the intensity of humans here is assigned a value of 0. Okay, so 0 decibels is you can't hear that sound. And not that there's no sound or there's no vibrations being produced, it's just inaudible due to human hearing. Okay, now the scale is logarithmic. What does that mean? That means it's in base 10. Okay, so just like the pH scale you probably learned in chemistry, all right, the decibel scale is in base 10. So each increase of 1 bell is 10 times louder. Okay, so if you have something that increases 3 bells, it's 1,000 times louder. Okay, and then if you take into account, well, a decibel, okay, is 10 times a bell, so that means an increase of 1 decibel would be 10 times 10, so that's 100 times. So that's the tricky part when you think about bells versus decibels. So try to keep those straight. All right. So here's an example of different things here. All right. So you've got your intensity, watts per meter squared, and here's your decibel levels. Okay. So like threshold of hearing is defined at 0. That's the quietest thing we can hear. Okay. And then up here like a thunder clap. Okay. This isn't a move that the Hulk does on Thanos. This is just a clap of thunder outside during a thunderstorm. Okay. Also, like I looked up online just out of curiosity, like cicadas, like here in the Midwest, we get every, 7, 14, whatever odd years, we get cicadas outside and they're freaking loud all the time. Okay. And they float around like 130, 140 decibels, like they can get that loud. And so it's like essentially having like a couple of machine guns in your tree during the summer sometimes. It sucks. But anyway, okay. So practice problem here. This is not too bad. Okay, it says the intensity of sound from an explosion is 0.1 watts per meter squared at a distance of 1 times 10 to the 3rd meters. Find the intensity of the sound at a distance of 500 meters, 100 meters, and 10 meters. All right, so we want to find intensity. Remember, intensity is equal to power over 4 pi r squared. All right, so if we want to find the intensity at these values, we need a power and we need a distance. Well, we've got our distances, but we don't have power. Well, we can use this intensity and this distance here in order to find that power. All right, so if we were to find power, we'd rearrange this formula. So our power would be equal to, we'll just multiply all this over. So it would be 4 pi r squared times I. All right, so it would be 4 times pi times 1,000 squared times 0.1. All right. So 4 pi 1,000 squared times 0.1. And I got 1.26 times 10 to the 6th. 1.26 times 10 to the 6th. And this is in power, so it would be watts. All right, so that's pretty easy. Probably too many sig figs, but that's not really our final answer, so we don't care that much. Now all we have to do is just take this power value and plug it in here to solve for our I. So for the first one, our I would be equal to 1.26 times 10 to the 6th divided by 4 times pi times our R value, which was this 500. Okay, 500 squared. All right, and we plug all that in. So divided by 4 pi times 500 squared. All right, and I got 0.4. All right, and 0. And then it would be watts per meters squared. All right, and then if you did the other three, you'd find answers like this. They got 0.41 watts per meter squared. I'm not quite sure how they got that, but maybe because I didn't round my answer in my thing when I found it. 1.26 e to the 6th divided by, that's probably what it is, 4 pi times 500 squared. Yeah. Anyway, so they got 0.41 watts per meter squared, and then at 100 meters it was 10 watts per meter squared, and then at 10 meters it's 1,000 watts per meter squared. Okay, so you can plug those in and solve for those yourself just to make sure it's all right. All right, so then it says find the approximate decibel equivalents of these sound intensities using table 2. Well, table 2 is right here. Okay, so the first one was at 0.41, right? 0.4. Okay, we'll just say 0.4 because that's the number we agreed on. I didn't know where they got the 1 from. But anyway, so if we were going to convert this to scientific notation, because this is in scientific notation, okay, we would convert it. It would be 4 times 10 to the minus first. Okay, well, minus first is right here, and this number is greater than that, so our number would be somewhere in here. So it would be at like 115 decibels, maybe 114 decibels. Okay. The next one was at, what was the next one? Oops, 100 watts per meter squared. So it would be here, so it would be at like 130. Okay, and the last one was at 1,000, so it would be 150. All right. So that's the how to convert between intensity and decibels. All right. So the softest sounds human can hear is called the threshold of hearing. All right, and it's where we already talked about this, where we have 0 decibels, and on that table 2 we saw that it was at 1 times 10 to the minus 12th watts per meter squared. The loudest sound humans can tolerate is called the threshold of pain. All right, no joke, I didn't make that up. I know you probably thought I did, but that's legit. Okay, that is a scientific term. All right, threshold of pain, pretty awesome. All right, and it happens at about 120 decibels, so that's where you can hear stuff and then it starts to hurt. All right, or causes long-term damage. Okay, now the human hearing depends on both frequency and intensity. So we've got this graph here. Okay, here's our intensity in our y-axis. Okay, here's intensity and here's frequency. All right, this region here, it's purpley-ish. Okay, this is all human hearing. This is kind of the general average. This is what we can hear. The bottom part of this curve, okay, all the way from this point all the way around the horn to this point, I would define as the threshold of hearing. All right, so notice how like we can hear sounds pretty dang well that are about like, what is this, like 2,800 hertz? Like we can hear this, but like over here at like you know, really low frequencies, we have a heck of a time hearing these at any sort of intensity. Okay. So anyway, and then up here we've got threshold of pain. Notice that low notes, we've got a lot higher threshold of pain, and this, I think this is about the volume at which that, you know, the character on Friends that laughs like crazy. I think she laughs somewhere in here, but anyway, it causes that pain. And we've just hits it with just enough intensity. Anyway, and so then the music region, okay, is this like greenish color, okay? So this is where music tends to be, and then speech region is in here, okay? Yep. All right, forced vibrations. Okay, now this is kind of, we're changing modes here a little bit, okay? Forced vibrations are these things that are called sympathetic vibrations, and they occur when a vibrating object forces another object to vibrate as well, okay? So this is essentially how a lot of musical instruments work, especially string instruments. So you think about a guitar, okay? So you got a guitar, it's shaped something like this, right? And it's got a neck on it as well. It comes out like this, okay? And then right here you've got a hole somewhere, right? And then you've got, you know, your strings go from here to here, right? And they kind of go like that. You strum your guitar. Now, you've all taken a string, like a piece of floss or a shoelace, held it real tight, had somebody strum it, and you can hear the note. Okay, guitars work on the same process, except for they have this thing here. Their body is this open sympathetic vibrator. Okay, and so when a note comes across and buzzes, you know, here, then it causes the entire body to start vibrating as well and makes this volume much greater. Okay, so this is really what allows a lot of these musical instruments to work, like guitars, pianos, violins, any sort of string instruments really rely on this a lot, this idea of sympathetic vibration. Okay. Now the other interesting thing is it makes the sound louder, but because the energy is being used to make something else vibrate, the string or whatever it is that is causing the initial vibration will not last as long. So this is one of the things that makes having a soundboard on a piano so important. Okay, without a soundboard, you would, number one, the strings would be a lot quieter because it wouldn't be nearly as loud, and number two, your strings would play forever. Okay, and so then all these notes would start to get muffled together and mush over themselves and be no good. Okay, so this is called sympathetic vibration, okay, or forced vibrations. Okay, so this leads us to this idea called resonance. Okay, now here in this example here, we've got this pipe, And we've got these different strings, and they're each attached by this red rubber band, and it links these 4 pendulums apart. If you take this blue pendulum and start sending it in motion, it's going to transfer this frequency at which it's this vibration, and based on its amplitude, to these other balls that are attached to this. Okay. Now the idea is, remember that based on a pendulum, okay, the period of a pendulum is equal to 2 pi times the square root of length over the acceleration due to gravity. Now we assume all these guys have the same gravity acted on them, but notice that their lengths are all different except for these 2 blue balls here. Okay, they've got the same length. Now because they have the same length, their fundamental frequency is the same. Okay, and now so this guy is going to start swinging back and forth, right? And so as he starts swinging back and forth, the green and the orange ones will also start swinging back and forth. Right? But the blue one will swing much more. And in fact, he'll start to match this blue one's frequency, because he's going to transfer and start forcing this other object to vibrate. And it works best because they have the same fundamental frequency, because they're both at the same length. All right? So finally, large amplitude vibrations produced when the frequency of the applied force matches the natural frequency of the receiver. Okay, this is the definition of resonance. So in our example, one blue pendulum was the driving force and the other one was the receiver. Okay, so there's your definition of resonance. And now resonance has a huge important thing. Okay, bridges have collapsed as a result of structural resonance. I suggest looking up the Tacoma Narrows Bridge. Okay, it went over the Bridget Sound or something like that. Okay, but anyway, in the wind, because of the wind that was hitting it, it happened just right at just the right frequency that it hit the resonance frequency of the bridge. And so the bridge started actually like twisting in the wind like this, like a roller coaster, and it eventually crashed. All right. Freeway overpasses during earthquakes. Earthquakes are shaking the ground. If they do it at just the right frequency, like, it can seriously damage and destroy these bridges. Okay, so here's just a screenshot of the Tacoma Narrows Bridge. Like, I know it happened in the 1940s. So notice you got this old school car that's out there, and this thing, like this, this is totally tilted at this wild 30-degree angle or so. It's wild. Okay. Anyway, so that's it for part 5, part 5, sound intensity and resonance. Do your practice problems. Let me know if you have any questions. All right, I'm here to help. Okay, so do your practice problems, and I'll see you on the flip side.